So for number 1, we have PERT, and we want to know at time 2 hours the concentration of the drug is 109 milligrams per liter. Use this information to calculate the value of dk. So I know that when t equals 2, y equals 150. So 150 is equal to, oh no, wait a minute. Not 150, 109. Sorry, this is 109 and this is 150. So 109 is equal to 150 e to the r times 2. So I'm going to divide by 150 and then ln both sides and drop the 2r. So I get the ln of 109 over 150 is equal to 2r times the ln of e. That cancels, and then I just divide this by 2. Yeah. So the ln of 109 divided by 150, and then we divide that by 2. Does that number make sense? Why does that number make sense? How did I know it was going to be negative? Well, it says we are looking for the decay constant. So there's a certain amount of drug, there are 150 milligrams per liter in there. They've turned off the machine that's giving them drugs, so eventually their body is going to metabolize all of the drugs in their system, and it will eventually be 0. So we're going down 15.9%. So it's dropping at 15.9%. Now, this is interesting. Will the drug ever totally be gone? Yeah, the decimal is 0.159, so the percentage is 15.9. So will the drug ever totally be gone? Mathematically, no. But the drug is made up of molecules. So you lose 16% of the molecules in the first hour, and then 16% more, until you get down to like 10 molecules. And then you drop to like 7. Then you drop to 5, and then 4, and then 3, and then 2. And when there's one more molecule in your body, eventually that one gets kicked out, and then there's nothing left. So mathematically, it will never equal 0, but practically in the real world, eventually it will all be gone. And at first it will be so gone, it'll be low enough that we can't measure it, and there's still some in there, but eventually it will all be gone. Okay, B. The next day the patient is given an injection of a different drug for which the concentration can be modeled by that, where C sub 0 represents the initial concentration, the exponent is negative 0.2 T. The doctor would like to take initial concentration to be large enough so that the concentration has a value of 90 milligrams per liter at 4 liters. How much do they need to inject? So Y equals PE to the RT. So at time 4, we want Y to equal 90. So how much do I need to stick in for that to work? Well, we just plug it in. 90 is equal to P times E to the negative 0.2 times 4. And this is all just a number, so I'm going to divide 90 by that. So 90 divided by E to the negative 0.2 times 4. And if you have the older calculator, make sure you use parentheses in the exponent. What does that mean? Second ln is the E button. That's P. That's how much needs to be given. If you get a shot with that much medicine in it, then you will still have 90 milligrams per liter at the end of 4 hours. 200. 200.2. All right. Yes. Well, and it's probably 200, right? They're just going to stick 200 in there and call it good. 2. Due to an increase in demand, a manufacturer of organic cereal is expanding its production facility. The number of kilograms and being produced each day will be increased to reflect the changing daily amount. After X days, the number of kilograms that will be produced each day will be modeled by that function from 0 to 100. Determine the inverse. So y equals negative 800 over x plus 1. The inverse is going to be x is equal to negative 800 over y plus 1. What should I do here? Put x over 1 and cross multiply. And that negative has to belong to something. So let's put it with the 800. So we'll cross multiply that. Negative 800 is equal to x times y plus 1. So I divide by x, and then I subtract 1. So y is equal to negative 800 over x minus 1. What is the range of the inverse? It's the domain of the original. Does the domain have any restrictions? Yeah, it told us what the domain is. It's from 0 to 100. So the range is from 0 to 100 with brackets. So the range is 0 to 100, like that. All right. What does the output of the inverse function represent? So in the inverse function, is the output x or y? It's y. What does the output of the inverse represent? Days, right. Because the input of the original was days, and when we do the inverse, days and production amount flip. All right, number 3. A producer of pesticides is going to begin production of a new maximum strength product. The total number of gallons produced after T days is given by N of T is equal to 4T squared. So N of T is equal to 4T squared. And the total cost associated with that is C of N is equal to 2,000 plus 2 times the square root of N dollars. So we can use T to calculate N, which is in gallons. So time can tell us how many gallons we're going to create, and we can use N to calculate C, which gives us the cost. Well, we want to skip the middleman using composition of functions, so which one do I plug into which? We're going to plug this in here. And that makes sense. If you look at the original functions, can I plug this into there? Can I plug a C equation into a T variable? No, that doesn't work. But we can plug an N equation into an N variable. And you have to show how you do it. That's pretty easy. So I get 2,000 plus 2 times the square root of 4t squared. What is the square root of 4t squared? Not, well, 2t, right? This becomes 2t, and then we times it by 2, so the answer is 2,000 plus 4t. So the square root of 4 is 2, and the square root of t squared is t, but there's also a 2 on the outside. So we take that 2t and we times it by 2. What does this equation do for us? Hang on. Maybe I'll find it. So what does this equation do? Well, the original equation took time and turned it into a gallon value, and then we turned gallons into cost. So the new equation goes straight from time to cost. Okay, what is the domain of the function? It's going to be from 0 to 30, right? Yeah. Yeah, in brackets. 0 to 30, both are brackets. Okay, using the results in part A, when will the cost be worth $2,100? We just set this equal to 2,100. Subtract 2,000 and we get 100 equals 4t. Divide by 4 and t equals 25. Got it? So when is the cost equal to $2,100? So I just plug that in for C. 2,100 is equal to 2,000 plus 4t. Subtract 2,000 and divide by 4. All right. And so we have the equation d of t is equal to 2t squared minus 8t plus 16. And I'm going from 0 to 6. At what time will the demand be at its minimum level? Well, let's factor this. So I'm going to divide by 2, and I get t squared minus 4t plus 8. Ooh, that doesn't factor. Okay, let's graph it. So 2x squared minus 4x plus 16. What should I put in for my x values? 0 to 6. They told me what the domain was. And then how do I choose my y values? Zoom 0, which is fit, and it will choose the y values for us. Okay, when does that minimum happen? Looks like at 1, but let's double check. So I'm going to go left bound 0, right bound 2, and my guess will be 1. So at 1 month, the minimum is 14 gallons. So 1 month is the minimum. At what time will the demand be equal to 26 gallons? So I want to know, when does this equal 26? Well, I'm going to subtract 26, and I get 2t squared minus 8t minus 10. Divide by 2, t squared minus 4t minus 5. That does factor into x minus 5 and x plus 1. So I get, well, I guess it's t, sorry. T equals 5 and negative 1. What do you think about that? Is 5 okay? Yes. Why? It's inside the domain window. Is negative 1 okay? No, it's outside. So negative 1 does not count. The answer is just 5 months. All right. According to this model, what is the minimum demand that the country will have? It's going to be 14,000 gallons because we got that off the calculator. Y is 14 and it's in thousands of gallons. Okay, last one. So you didn't have the equation on this test, but its magnitude is equal to 2/3 log of E over 10 to the 4.4. And that will be, it was on the test, but it's just, it was on a reference page that I didn't print for you. Sorry. Okay, so one city has an earthquake that is measured at 6.4, and the other has an earthquake that's measured at 3.2. Is the city A earthquake twice as big as the city B earthquake? No, it's going to be much, much more than that. So what we need to do is calculate E twice, one for 6.4 and one for 3.2. So 6.4 equals 2/3 log of E over 10 to the 4.4. So I'm going to do um, times this by 3 over 2. And then I'm going to say 10. Well, I'm trying to do a shortcut. Let's not do it that way. So 60 times 3.2 is 192 is equal to log base 10 of E to the 4.4. Now I convert to exponents. That's 60. Oh, not 60. I'm sorry. It's 6.4 times 3 halves. Wow, I was way off. How about 9.6? Now I do 10 to the 9.6 is equal to E over 10 to the 4.4, which means I just times by 10 to the 4.4. So 10 to the 4.4 times 10 to the 9.6 gives me an energy of 1 e to the 14th. Now I need to do exactly the same thing with 3.2. So 3.2 raised to the, nope, times, sorry. 3.2 times 3 halves is 4.8. So I can do the exact same calculation I did before, but I'm going to replace 9.6 with 4.8. So I go up here. I'm going to duplicate that. And I will say 4.8. And I get that number. Now, how do I figure out how much bigger the first one is from the second one? Divide them. So 1e to the 14th divided by the answer, and it is 63,000 times bigger. Okay, hold on. Last two. If an earthquake has a Richter scale that is twice as large as the second earthquake's value, the intensity of the first earthquake is twice as large as the intensity of the second. False. We just showed that's not true. If an earthquake has a Richter scale value that is twice as large as the second earthquake, the energy released by the earthquake is twice as large as the energy released by the second earthquake. False, for the same reason.